So welcome to our first colloquium at The Ohio State. This is our first online colloquium and our first colloquium of the semester. And today I'm very excited to welcome Kenneth Falconer from the University of St. Andrews. He was at the University of Bristol before being appointed professor at St. Andrews. Professor Falconer was elected Fellow of the Royal Society of Edinburgh and was awarded the Shepherd Prize of the London Mathematical Society in 2020. Congratulations. His main research interests are in fractal and multifractal geometry and geometric measure theory. He's written 5 books and spoken at many major international conferences on fractal geometry analysis. And today, we're lucky he's speaking to us about symmetry and enumeration of fractals.
Okay, well, thank you very much for that introduction, Crystal. Can you hear me?
Yes.
Good. Well, good afternoon, everyone there in Ohio. It's good evening from here. It's 9:15 in the evening on a rather wet evening in Scotland. But it's a great pleasure and honour to speak at the colloquium of the Ohio State University Mathematics Department. So thank you very much for asking me. I'm going to talk about some work I did a few years back now with a colleague, John O'Connor, involving symmetry and enumeration of self-similar fractals. But in fact, I've sort of resuscitated the project a little recently. I've had a couple of undergraduate vocation students looking at some more examples. So it's, from my point of view at least, it's quite timely. So let's start by looking at some self-similar fractals. And I'm sure these are very familiar: the Sierpinski triangle, the Sierpinski carpet, there's a snowflake fractal, and there's a spiral fractal. And these are all self-similar in the sense that each is made up of, can be decomposed in into a number of pieces which are each similar copies of the whole, just with Euclidean similarities, and the whole is made up, or the Sierpinski triangle is made up of 3 copies of itself at scale 1/2. This spiral is made up of 2 copies of itself, one large one there that's slightly rotated and one very much smaller one there. So these are self-similar fractals made up of many smaller copies of themselves when you iterate the constructions. Let's start by thinking about a very basic self-similar set, namely the middle third Cantor set in the unit interval, which of course is obtained by starting with the unit interval, removing the middle third, the open middle third, and then removing the open middle third of the parts you've got left, and continuing like that ad infinitum. So at the k stage of the construction, you've got 2 to the k intervals of length 3 to the minus k, and taking the intersection of all those, we get the middle third Cantor set, which, if you like, you can essentially think of it as those numbers between 0 and 1, whose base 3 digits, base 3 expansions only include the digits 0 and 1. Sorry, 0 and 2. But the thing I'd like to note is that this middle third Cantor set is made up of 2 copies of itself at scale 1/3, a left part and a right part, which are both similar to the whole. And we can express that in symbolic terms. So if I write down functions from the reals to the reals, or from the unit interval into the unit interval, the first simply shrinks by a factor of 1/3 about the origin. The second does the same and then shifts along by 2/3. So if I take the middle third Cantor set, then F1 of the Cantor set is the left part, F2 of the Cantor set is the right part, and so the middle third Cantor set is the union of its images under F1 and F2. So that's another way of expressing the self-similarity of the middle third Cantor set. And it turns out the interesting thing is the Cantor set is completely determined by this identity, that it's the image of itself under the union of the image itself under these two transformations there and there. That's obviously not strictly true, because the empty set also satisfies that, as does the whole of the real line, but it is the unique non-empty compact subset of the line that satisfies this condition. And this is a special case of something more general, namely if I take some closed domain in n-dimensional Euclidean space and a family of contractions f1 up to f little n, mapping that domain into itself. So they're contractions. That means that the distance between the image of 2 points under any of the mappings is no more than a constant less than 1 times the distance between the original 2 points. If a family of contractions of that type is known as an iterated function system, which is abbreviated to IFS. And these things are, iterated function systems, are central in the study of fractals. And one of the reasons for that is there's a lovely theorem which was formulated in this way back in 1981 by John Hutchinson. And this says, if you're given an iterated function system of contractions satisfying this condition, then there exists a unique non-empty compact subset of the domain E, which equals its union, the union of its images under the contractions that are given. And there's a very elegant and short proof of that, which I must include, it's too nice to omit, using Banach's fixed point theorem, Banach's contraction mapping theorem. If you look at the map that takes any non-empty compact set A to the union of its images under the Fi, since the Fi are contractions, you can show that this transformation there is a contraction on the space of non-empty compact subsets of our domain D. And that's a contraction with respect to the Hausdorff metric, which is a natural way of expressing the distance between two sets. And the Hausdorff metric is complete. The fixed point theorem tells you that a contraction on a complete metric space has a unique fixed point, and that's the proof. So that's rather lovely, I think. And this set satisfying, this non-empty compact set satisfying this identity is called the attractor of the iterated function system. And in particular, if these contractions are actual similarities, so that means that the distances are all multiplied by a constant for each Fi. So you've got a fixed scaling for each mapping Fi, then you refer to the set, the attractor set E, as self-similar. So the set E is made up of a union of similar copies of itself at smaller scales. So here's another example in 2 dimensions. The right-angled Sierpinski triangle. You can see obviously it's made up of these 3 copies of itself like that, and you can write down the mappings in this way. They're all contractions of ratio 1/2, and the whole right-angled Sierpinski triangle is the union of these 3 scale 1/2 copies. And I'm going to superimpose a sort of template on that. There's a large red square, the unit square, and then there are 3 squares, blue squares of side 1/2 that fit together in the obvious way. And what we're seeing is the entire image is the union of the scale copies that you get by the similarity mapping that takes the whole unit square onto each of these 3 squares. And so we can remove the Sierpinski triangle and retain the template. And so that template is a sort of way of representing an iterated function system. I say I want similarity transformations that map the whole of the large red square into the 3 smaller squares. However, things aren't quite as simple as they might first seem if I'm just thinking about similarity transformations, because there's not a single similarity transformation that maps the large square onto this bottom left-hand square, but there are in fact 8 different similarity transformations by virtue of the symmetry group of the square. I can rotate through 0 90, 180 or 270 degrees. And I can also reflect in the horizontal and vertical axes or the two diagonal axes. So in fact, there are 8 similarity transformations that will take the unit square onto each of the 3 smaller squares. And it's that variety that are going to inform us in what we're going to be doing over the next few minutes. So the setup we've got, and I'm going to take this example as a basic example. We've got a unit square, which I'm going to call D, and we've got 3 subsquares, D1, D2, D3, arranged like that in a scale of side 1/2. And I'm looking for 3 similarity transformations of ratio 1/2 that take the big square onto the first, second, and third smaller squares. And so that gives us an iterated function system consisting of 3 similarity transformations, and that gives us an attractor, which is the union of the whole thing under these 3 mappings. But as I've indicated, there are 8 possible choices for F1, F2, F3 to map the whole picture onto the smaller squares. And that means we've got 8 choices independently 3 times, so 8 cubed or 512 different iterated function systems, different triples of similarity transformations that correspond to this template, if you like. So we've got 512 triples that we can pick from. So here are 2 possible attractors, just choosing 2 particular triples of transformations. And you can see here you've got this black self-similar set. The bottom left-hand corner is a direct scale down of the whole thing. But if you look at these 2, you've rotated the whole picture to 180 degrees before scaling it down, or if you prefer, you've reflected in the downward diagonal to get that. And similarly, here's another example. Again, you can see the entire attractor is made up of 3 half-scale copies of itself, but here you've got a reflection rather than a direct reduction in scale. So what we're interested in is how many different attractors we can get corresponding to a particular template, and what can we say about their symmetries. This example, you've got reflective symmetry in the upward diagonal. Here you've got no Euclidean symmetries at all that map the, no isometries that map the whole thing onto itself. And note that in this case, as I pointed out, there's more than one choice of triple of the 3 similarity transformations that map the whole picture onto each of these pictures. So here I could just shrink down directly, or I could reflect about the upward diagonal as I was shrinking down. So that's the question we're going to be interested in. And it turns out for this example with the unit square and the 3 half-side squares, in fact, there are 8 different attractors which have this diagonal reflective mirror symmetry. We've seen a couple of them already, including the right-angled Sierpinski triangle. Here are 3 more of them, and the colouring indicates the 3 smaller copies of the whole thing that put together in the appropriate way make up the original set. And so I claim that there are 8 actually possible attractors that you can get from that template with this diagonal symmetry, and these are shown here, and each is the attractor of 8. I can choose 8 different triples of similarity transformations to define any of these with this mirror symmetry. And then that accounts for 8 times 8, 64 of the iterated function systems, which leave 448 out of the 512. And all these remaining 448 have there are no non-trivial isometries mapping the sets onto themselves. There are no Euclidean symmetries that these examples have. Those are just 3 of the very large number, well, the 448 without a reflective symmetry or any rotational or reflective symmetry. And each of these there's only one triple of similarity transformations that will yield each of these. So that's an outline of what we want to analyse, how many different sets we get from a template, and what can we say, are they symmetric in any way or not. So this is the aim, what I'm going to discuss the rest of the talk, given some region D and a family of iterated function systems, counting the number of different attractors and seeing what we can say about their symmetries. So let's put this in a general setting, but I am going to keep this three small squares and a big square as an illustrative example as we go through. So keep that at the back of your mind. But in fact, all we need is some domain D in n-dimensional Euclidean space, and D itself should have some symmetry. It could be a square, as we've seen. It could be a hexagon, a cube, or something like that. And I want D1 up to D little n to be similar copies of D, all scaled by the same ratio, fixed ratio R. In our example, it was a half. And I want them to be arranged inside D so that their interiors are disjoint, and I want them to be similarly orientated. So the positioning is a direct positioning under a symmetry of the larger square. And I also want to assume that if I take the union of these smaller regions DI, so this in this case is this L-shaped block, that the union of these full squares has some of the symmetries of D. So in this example, the symmetry group of the square is order 8, and if I look at this L-shaped figure, that has two symmetries of those 8, namely the identity and reflective symmetry about that leading diagonal. So that's what we're interested in, and this can be considered in a much more general setting. And so given domains, large domain D and small subdomains D1 up to Dn, I'm going to write script C of D for the family of iterated function systems, namely interpals of similarity transformations where that should be F1 up to Fn map the big domain D on Fi maps it onto the subdomain Di, and I want these to be similarities. Then because the domain capital D has the symmetry, if that has symmetry group of order D, then I've got n subregions. So I've got D to the n different interpals of similarity transformations that are in this family. And these D to the n iterated function systems may give different attractors, but not all combinations will give different attractors. Very often there are different combinations of similarity transformations that yield the same attractor. And so that's where this analysis starts to become interesting. So let's start with a simple lemma. Suppose I've got two interpals of similarity transformations in this family for a domain D. In other words, two iterated function systems that both give the same attractor E. Well, that will happen if and only if each the Fi primed is a symmetry of the attractor left multiplied by Fi. So if you know what the symmetries the attractor generated by an iterated function system has, then any other iterated function system that gives the same attractor, you get the Fi prime simply by taking one of the symmetries and left multiplying by Fi. And in particular, that means that since you've got little n similarities and you've got a choice of any symmetry of E relating Fi and Fi prime, that means precisely the order of the symmetry group of E to the power n of these n-tuples will yield that attractor E. And the proof of this is very easy. If E is the attractor of these two iterated function systems, then it's the union of its images under Fi, and it's also the union of its images under Fi primed. But because these domains had disjoint interiors, and Fi of E and Fi primed of E lie in the same domain Di, the same part of the picture, that means that if these two pictures are the same, then the part of the picture inside each Di has to be the same. So if we've got those sets are equal, then that means that for each I, Fi of E has to be the same as Fi primed of E. So that's just, if you like, decomposing these unions inside each of the smaller regions. And now once we've got that, it's simply manipulating the transformations. So I take the Fi onto that side as an inverse, and so E is its image under the composition of Fi primed and Fi inverse. And so that means that Fi primed followed by Fi inverse maps E to itself. In other words, is an isometry or symmetry of the set E. And so using sort of coset notation, that means Fi primed is there's a symmetry of E left multiplied by Fi. So it's a very simple proof of that. The trouble is this, with this lemma, is that to be able to say that two iterated function systems give rise to the same attractor, you first have to know what the attractor is. And so you can see whether it's what its symmetry group is. So that's not so much use if you start with an iterated function system and you want to know which other iterated function systems give the same thing. You need to find the symmetry group first. So what we really want to know is to identify iterated function systems that give rise to an attractor with a particular symmetry group. So we next need to try and address this. So that's what I was saying. We need to know what the symmetry group is. And what we really want is a characterization of iterated function systems whose attractor has a given symmetry group H. So to analyze symmetries, one obviously tends to use group theory. And so we're going to start introducing a bit of group theory to help us with this problem on finding symmetry groups of these attractors and counting them. So I've got my large domain D, which has some symmetries. I'm going to write G0 for the symmetry group of D, and I'm going to write G for the symmetries of the union of these other regions. I said I wanted to retain some of the symmetries of the whole region with the union of the smaller regions. So in this basic example, G0 is the D4, the group of symmetries of the square, group of order 8, and G I'm going to take to be the two-element group consisting of the identity and the reflection and the leading diagonal, and that's the group of symmetries of the union of these three squares, the identity, or it'll map to itself if you reflect in the leading diagonals. So that's what we've got in this case, and so we've got this large group G0 and the smaller group G. And note that a symmetry, little g, a symmetry of G, so that's of the smaller group, that induces a permutation, which I'm going to call G star, of the smaller regions. So, regions are numbered 1 to n, so essentially that's a permutation of the integers 1 to n. So if you take little g to be the reflection in that leading diagonal, squares D2 and D3 get swapped, D1's fixed, so that corresponds to the permutation 1, 2, 3 goes to 1, 3, 2. Okay, and so we have another lemma which starts to enable us to identify the symmetry group of a given iterated function system. So for an iterated function system f1 up to fn, an interval of similarities, if E is the attractor, then G will be a symmetry of E precisely when, if I look at the composition, do Fi first, and then do G, and then do the inverse of F, where the subscript is what G takes the ith subdomain to a new subdomain. So G star I is the transformation on the subdomains or the indexes of the subdomains that I've just mentioned. So that is a characterization of, given the iterated function system, it tells us by doing this check, we can find whether we've got a symmetry G. So to prove this, again, it helps if we look at a picture, but it's a straightforward proof. If G is a symmetry, so imagine this attractor pictured there, which has reflective symmetry in the leading diagonal, then what does that say? Well, if you've got reflective symmetry, what you see in that square over there has to be reflected, and that will give you what you see in that square over there. So that means that for all I, if I look at Fi of the whole attractor, which could be that bit, and then do G, then apply the symmetry to that, that will give me an image over there in the square or the subdomain G star I, and what I see in that subdomain, the smaller copy in that subdomain, simply has to be the image of E under the map FGI star. So for each I, we've got to have this relation there. In our example, obviously, since the reflection in the upper diagonal just takes this bottom left square to itself, then that simply means that G has to be a symmetry of G F1. It has to be the same as F1. GF1 of E has to be the same as F1 of E. So we've got that for all I, and now again, we just take everything onto the other side. We take FG star I over to the other side, and that's got to map the set E to itself. So in other words, this composition of mappings has to be a symmetry of E. So this tells us when G is a symmetry of the set E. And that leads on to the way we think about the group theory to analyze these things. So given a group G, a subgroup H of the form we've been talking about, and an iterated function system F1 up to Fn of our similarities, given H a subgroup, I'm going to define H primed, which will depend on these Fi, by the following formula, namely it's the elements of G such that if I look at this composition, Fi followed by G followed by G star I inverse, that composition belongs to H for all I. So I'm looking at those elements of the group G such that when I look at that composition, I end up in H. I was tempted to call H prime the derived subgroup of H, but I believe that term's used for something else, so I better not call it that. It's not difficult to see that starting with a subgroup H, then H primed will also be a subgroup of G, but also the prime operation preserves subgroup inclusion. So if H1 is a subgroup of H2, then H1 prime will be a subgroup of H2 primed. And that means that we can think of a series of groups. So if I start with G and prime G itself and prime under this operation, I will get a subgroup G primed. And so I can then prime again, and G prime primed will be a subgroup of G prime, which will be, and since G prime primed is a subgroup of G prime, just using subgroup priming, preserving subgroup inclusion there, I get a decreasing series of subgroups of G in this way. So starting with my iterated function system, I can define a sequence, a series of subgroups in this way. And because we're only working with finite groups, eventually we're going to come to a point where the series stabilizes, where we just repeated priming just leaves us where we are. And it turns out what you get to by this repeated priming process, when you stabilize, the group you get is the symmetry group of the attractor. So that needs a little bit of proof. So in particular, the symmetry group primed is itself. And writing that in a slightly weaker, apparently weaker way, that means the symmetry group is a subgroup of its prime group rather than the other way round. And that leads to the second part of the theorem, which says, in fact, the symmetry group is the maximal subgroup of G for which you get this condition, get this inclusion this way around. It's the maximal subgroup that is a subgroup of its own primed, given its own prime group, given the iterated function fi. This is more useful for what we want to do, namely, given a potential symmetry group H, we can look for iterated function systems f1 up to fn, such that H is the maximal subgroup satisfying this. And so basically, this reduces the problem of enumerating attractors with given symmetries to a problem that's reasonably tractable in group theory. I hope that makes some sort of sense. Well, how do we do, we want to be able to check this condition, and it turns out that this isn't, there's a nice way of doing this using orbits and stabilizers. So recall that if you've got a collection of objects that acted on by a group, in particular, I'm thinking of the subdomains di, or the indices representing the subdomains I, then for our group H, or the induced group on the integers 1 up to n, the orbit of J is simply the set of I which you can get to under one of the mappings H, or H star is essentially the same thing in the subgroup H. That's the orbit of J under H, and the stabilizer of J in H is simply those H that map J to itself, or H star maps J to itself, simply since we're looking at the indices or the domains di, dj. So we've got the usual orbit and stabilizer there effectively. And there's a nice criterion. You remember, we have to look for subgroups H that are subgroups of their prime groups for a given iterated function system. It turns out that this condition is satisfied if for every orbit of our set 1 up to n, squares, domains D1 up to Dn, we have two conditions holding. Firstly, for any, you can choose some J in the orbit, and then there's the stabilizer condition. The conjugate of the stabilizer by Fj has to be a subgroup of H for some chosen J, and then for all other indices in the orbit, Fi, corresponding to the other I in the orbit, is of the form some element of subgroup H followed by Fj followed by some H you can choose that maps J onto I, or the star map takes J onto I. So this is actually a reasonably checkable condition to these two conditions, and we'll see in a moment, that characterize this condition, which is the thing we need to look at to find the symmetries and of the attractors of this iterated function system Fi. And there, in fact, is a more general version of this lemma which characterizes when you have this occurring for two different subgroups simultaneously. I'm not going to bother about that. So that's really the criteria that we can use to check similarities. And I'm now going to show, by means of an example, I hope, how this can be applied, by means of several examples, in fact. So still staying with squares, but at this time I'm going to split my unit square into 9 squares of side 1/3 in the obvious way, and I'm going to select the 3 squares in the columns on either side as my subdomains, and I've got 6 subdomains which I've labelled in that way. And so I'm interested in the iterated function systems of similarities, so sextuples of similarities that map the unit square onto each of these side squares, and remembering that for each of these smaller squares I've got 8 choices of orientation of the similarity mapping from the large square to the smaller square. And in this setup, so the large group I was referring to before, G0 is the dihedral group D4, simply the symmetry group of the square. And now the smaller group is D2, the group of order 4, because you can map the union of these 6 squares onto itself by the identity by a vertical reflection, a horizontal reflection, or a 180-degree rotation. So you've got the smaller group is of order 4. And so one can look for attractors where the symmetries are subgroups of D4. And here's some examples here. 3 of these examples, in fact, that one, and that one, have full order 4 symmetry. Horizontal vertical reflection, 180-degree rotation. Here's an example which just has order 2 symmetry, reflective symmetry in the vertical. Here's an example which has reflective symmetry in the horizontal only. And here's an example which has 180-degree rotational symmetry. And here's an example which has none of the symmetries at all. Okay, well, how many iterated function systems of 6 similarities are there? Well, I've got 8 choices for each. That's 8 to the 6. That's just over 250,000 different iterated function systems that map that square onto each of the combinations onto the 6 subsquares. So that's rather a lot. And it turns out, using calculations, a lot group theoretic calculations that I've indicated, there are only 4 attractors which have the full order 4 symmetry, and you've got 3 of them there. There are 32 which has the horizontal order 2 symmetry. There are also 32 that have vertical reflective symmetry, and there are 32 that have 180-degree rotational symmetry. It almost seems that the fact that you get 3 32s is coincidental, because the calculations you have to do in each case are a bit different. And so that leaves a 239,000 attractors, all different, which have no symmetry at all. And so the total number of different attractors you get by summing that lot. So let me just indicate how one of the calculations works. Let's try and indicate how we can count up the number of different attractors, fractals we can get this on this template with horizontal reflective symmetry. So this is the picture of the subdomains. I've numbered them that way, and we're interested in the horizontal subgroup horizontal reflection subgroup consisting of the identity and reflection in the horizontal. And so, as I indicated before, we have to look at the orbits of the squares under this subgroup. So we've got the identity, or we've got reflection in the horizontal. So 1 can go to 3 under these two elements. The identity leaves 1 where it is, the reflection takes it to 3. So 1, 3 is an orbit. Similarly, 2 to 4 is an orbit. And then 5 just gets fixed by both of the elements in this group, the identity and the reflection. So 5 is an orbit by itself, as is 6. So we've identified, we've decomposed our smaller domains into orbits in that way. And we can identify the stabilizer. Well, for the orbit 1, 3, the stabilizer is the identity. Only the identity in this group fixes 1. So this condition in the lemma we just had, that the conjugate of the stabilizer by Fj, it has to be a has to be in this, has to be the subgroup of H, is trivially satisfied for all Fj because the stabilizer is the identity. So that condition is satisfied for F1, say, for any F1 in the order 8 group, in the big group. But having done that, I now have to look at F3, which is the other term in this orbit, and 3 is in the orbit. So F3 has to be of the form something in the subgroup H acted on by F1 and then multiplied by any H that takes the index 1 to the index 3. So F3 is constrained by that once I've fixed F1. And similarly for the orbit 2, 4, F2 can be anything in the any of the 8 possibilities, but once you've done that, F4 has to be of that form, so there are just 2 possibilities left for that. And similarly for these other 2 orbits, the stabilizer is H, so we have to look at which of the 8 possibilities for F5, the conjugate of H is H itself. Once we've done that, that's the condition for F5. It turns out, I won't go through the details here, F5 can be anything in the order 4 group, D2, so that's vertical and horizontal reflections and 180-degree rotation. And then nothing else in the orbit, so I've got no further conditions there. And similarly for the 6th mapping. So that's what the group theory tells us. And now we can simply count up the number of sextuples F1 up to F6 that satisfy the conditions for H to be a subgroup of H primed corresponding to the iterated function system F1 up to F6. And we've just got to go through this table. We've got 8 possibilities for F1, that can be anything. And given those, we've just got 2 possibilities corresponding to the elements of H for F3. So that's an 8 times 2. Similarly, for F2 and F4, there are 8 possibilities for F2, and just 2 possibilities thereafter for F4. And now F5 can be anything in D2, so there are 4 possibilities there. F6 can be anything in D2, 4 possibilities there. So that gives 4,096 sextuples that satisfy these conditions, and therefore that give this condition for the subgroup H. Now we're not quite there because H has to be the maximal subgroup satisfying this, and it might not be because H is a subgroup of D2, the larger group, and we might have that being satisfied as well. So you have to do the same sort of thing for this order 4 group, and it turns out that 2,048, exactly half of these sextuples have both of these things satisfied. So only half of them have H, the maximal subgroup with this property. And so that means 2,048 sextuples, iterated function systems, have attractors with horizontal symmetry. And you remember that if we've got order 2 symmetry, then that gives us two choices for each of the mappings that will give the same pictures. We've got 6 choices of mappings, so 2 to the 6 different sextuples will give the same pictures. So I have to divide by that number to get a total of 32 distinct attractors. So that's the way we use the group theory to analyse these, the number of attractors. Let's look at another example or two. We can start with a hexagon and 3 subhexagons arranged like that. And we've now got the symmetry group of the hexagon has order 12. And if we take the union of these 3 smaller hexagons, then the symmetry group of that figure is order 6, 122, 140 identity rotations, and then reflections about 3 lines. And so we're in that setting. And so we've got 12 choices of similarity transformation from the larger hexagon onto each of the smaller ones. So that's 12 cubed, 1,728 different triples that are allowable similarities for our iterative function system. And if you do the same sort of calculation as before, it turns out that there are just 2 attractors, namely that one and that one, with the full order 6 symmetry. Then for each of the principal axes, there are 32 attractors which have reflective symmetry. So that one, for example, and that one have reflective symmetry in the horizontal axis, and obviously similarly for the other 2 principal axes. And then that leaves 1,040 iterative function systems which have attractors with no symmetry. And again, these are achieved, there is just a unique triple of similarity transformations which will give the remaining 1,040. So that's a different example. And then we can go over into 3 dimensions, and like it's a little bit more complicated here. So if we take a unit cube, split it up into the natural 8 subcubes, and then you take one corner cube and the 3 cubes that are adjacent by face to the corner cube. And we can look at the mappings from the unit cube onto these 4 subcubes. And so if we do that, if you allow not only the rotational symmetries of the mappings of the cube onto itself, but also the reflections, then that group has order 48. And on the other hand, if you take this union of 4 cubes with this sort of corner arrangement, then that figure within the main cube, that just has a group of symmetry of order 6, namely rotational symmetry against around the leading diagonal of 120 and 240 degrees, as well as the identity, and then reflection in 3 planes. So we've got the situation where the large group has order 48 and the small group has order 6. So because the cube has order 48, and we've got 4 cubes that we're interested in, the mappings from the large cube too, there are over 5 million, or 48 to the 4th, different quadruples of iterative function systems to consider. And if you do the analysis again, it turns out that you get 8 attractors which have the full order 6 symmetry of the triple of blocks. Then you get 32 with rotational symmetry about the leading axis. And for each of the plane reflections, you get 360 different pictures. And then that still leaves well over 5 million attractors which can arise from a unique iterated function system of 4 similarities in 3 dimensions. So you're already getting fairly large numbers. So that's sort of the illustration of a higher dimensional version of this sort of argument, looking at the iterated function systems of these classes, mapping a large domain onto small domains, and looking at the symmetries and trying to count the number of different attractors with the different symmetry groups. So let me end, and I hope this is going to work. I want to show, I know these pictures of the attractors in this case, it's not very easy to see what's going on. You're just looking at an end-on view. So I've got some little movers which might make this a little bit clearer. I hope the internet speed is good enough for you to see these moving fairly smoothly, and so you can get a better idea of what some of the attractors in this cube example look like. So let's start with an example which gives the Sierpinski tetrahedron. I hope you can see this moving around, which gives you an idea of what it looks like. So this is the right-angled Sierpinski tetrahedron as one of the attractors you get there, and that has the full order 6 symmetry. Then there's another one with the order 6 symmetry, which I call the square claw. Again, you can see it moving around to give you an idea of what it looks like. You've got the rotational and the reflective symmetry in the principal plane. Sorry, there it is again. I hope these are coming across reasonably well. Then there's another one with the full symmetry, a tripod, or a little flower if you like. Again, you've got the reflective and the rotational symmetry. Then here's an example with just plain symmetry, plain reflective symmetry. You can think of it as a sort of tree. Looks like that, where you now haven't got the rotational symmetry about the leading diagonal. There it is again. And while we were playing around with these examples, one which we suddenly encountered was this one, a flat triangle, which we didn't expect, but once you've seen that it exists, then it's perfectly obvious that it's got to be one of the possibilities, reflecting the bottom left corner cube and reflecting the other cube. So that actually has to be one of the attractors, very special case. And then finally, there's a claw, I think. Again, this example has full symmetry, and it's one of the examples that come from the cube template, if you like. So there it is again, just to give you these, just to give you some sort of visualization for the 3-dimensional examples, which are quite hard to picture just from a plain projection. So that's what I wanted to talk about. I hope it was of some interest. The original paper where we looked at this was in the Bulletin of the London Mathematical Society in 2007. But as I say, some undergraduate vocation students have been looking at some different examples, slightly more complicated examples from this sort of analysis. So thank you very much for your attention. I hope you enjoyed and got something out of this talk.
Thank you, Professor Falconer. It's really neat to see how group theory comes into your analysis. So maybe I'll get the questions started. What happens if we replace these iterated function systems with other groups of transformation? For instance, maybe you could look at symmetries. Oh, symmetries arising from fractals based on lattice tilings.
So what do you have in mind?
Just more general groups of transformations.
Yeah, I mean, there's no reason why you can't do the same sort of thing. I mean, we've played around with, you know, looking at examples based on a rectangular grid. So you're looking at affine transformations and so on. And again, you know, the same sort of ideas certainly work. Yes.
So I'd like to open it up to questions.
So let me try one. I was sort of curious, when you create a fractal, you can do it either by the set theoretic description that you gave, or a dynamical systems one where you really just iterate, randomly choosing each of the members of the iterated function.
Yeah.
You know this very well.
Yeah, the chaos game as it's known, I believe.
Yeah, and what I was curious is when you have two attractors which are the same in your context from the set theoretic way, are they the same dynamically in the sense that you can create an invariant measure, construct one for each of the two different attractors? Would you get the same measure, the same coloring, if you wish?
Well, I mean, obviously, you can define the, that there is a common invariant measure, but if you assign the same weight or same probability to each of the three squares, if you like, but also if you assign different weights to the three squares, then you will get different measures in each case. Yes.
Right, and just, can you correlate that with your counting of the number of iterated function systems that give you the same attractor?
Yeah, I mean, I think, well, in general, and well, I'm sure there'll be exceptional cases, but in general, if you have different probabilities, then the different iterated function systems will give different measures. Unless okay, if you have two of the probabilities the same and one different or something like that, then it can get more complicated. Right. Yeah, I would imagine if one had that sort of setup, so the bottom right and top left, well, if two of the regions had the same probability assigned to them, then yeah, you might want to count the different probability measures, I suppose, and I imagine this sort of analysis would extend to that, though I certainly haven't tried.
Thank you. It was beautiful talk.
Anyone else like to ask questions? All right, if not, thank you very much for this nice talk, and have a good night in
Well, thank you for inviting me. It's a great pleasure. Oh, I think there's a hand up somewhere. Oh, is that? Oh, okay, right. It's clapping. Okay, thank you very much. Okay, then. Have a nice, well, it's still afternoon there, I suppose, or late afternoon. Have a good evening. Right, cheers.